Imagine walking through Rome today and standing before the Pantheon, a building completed nearly 2,000 years ago. Its massive concrete dome, the largest unreinforced concrete dome ever built, still stands perfectly intact. No cracks, no crumbling. No repairs needed. The dome spans 143 feet across, and at its center is an open hole called the oculus, which lets in rain and sunlight. Yet the structure hasn't budged in 2 millennia. Now think about the concrete sidewalk outside your house, the one that started cracking after just a few decades. Something doesn't add up, does it? How is it possible that an ancient civilization without modern chemistry, without computer modeling, without any of the tools we take for granted, managed to create a building material that outlasts anything we produce today? The answer is one of the most fascinating mysteries in materials science, and scientists are only now beginning to understand it. To appreciate what the Romans achieved, you need to understand what concrete actually is. At its most basic, concrete is a mixture of some kind of cement, water, and an aggregate like rocks or sand. The cement acts as the glue that holds everything together. Modern concrete uses something called Portland cement, which was invented in 1824 by a British bricklayer named Joseph Aspdin. He heated limestone and clay together in a kiln, ground the result into a fine powder, and created the binding agent that essentially built the modern world. Portland cement concrete is strong, cheap, and incredibly versatile. Skyscrapers, bridges, highways, dams, almost everything in the built environment relies on it. We pour roughly 30 billion tons of concrete every single year, making it the most widely used manufactured material on Earth, second only to water as the most consumed substance of any kind. But here's the problem. Portland cement concrete has a shelf life. It begins to degrade almost from the moment it's poured. Tiny cracks form as it cures, a process called shrinkage cracking that is essentially unavoidable. Water seeps into those cracks and freezes in winter, expanding and making the cracks worse. Salt from roads or seawater accelerates the chemical breakdown. Rebar inside the concrete rusts, expands, and pushes the material apart from within. The American Society of Civil Engineers has estimated that the United States alone needs to spend trillions of dollars just to maintain and repair its crumbling concrete infrastructure. The typical lifespan of modern concrete is about 50 to 100 years, and that's with maintenance. Roman concrete, by contrast, has lasted over 2,000 years, and in some cases it's actually gotten stronger with time. The ancient harbor at Caesarea, built by King Herod around 25 before the Common Era using Roman concrete techniques, has spent 2 millennia submerged in corrosive saltwater, and the concrete is in remarkable condition. The Colosseum, though partly dismantled for building stone over the centuries, still has its original concrete foundations fully intact. Roman aqueducts, sewers, and foundations across the former empire continue to function, or at least remain structurally sound. So what was their secret? The Roman recipe was fundamentally different from ours. Instead of Portland cement, Romans used volcanic ash, specifically a type found near the town of Pozzolani in the Bay of Naples. They called it pulvis putiolanus, and we now call it pozzolanic ash. They mixed this volcanic ash with lime, which they produced by burning limestone in large kilns, and seawater. For aggregate, they often used chunks of volcanic rock called tuff. The Roman architect Vitruvius wrote about this recipe in his famous treatise on architecture around 30 before the Common Era, noting that structures made with this mixture became incredibly hard and resistant to seawater. He specifically marveled at how the material seemed to turn into a single mass of stone once submerged in the ocean. For centuries, scientists knew the Roman recipe was different, but couldn't fully explain why it worked so well. The breakthrough came in 2017 when a team led by geologist Marie Jackson at the University of Utah published a landmark study. Using advanced X-ray techniques at a particle accelerator in Berkeley, California, they examined samples of Roman marine concrete at the molecular level. What they found was astonishing. In modern concrete, the chemical reactions that form the material essentially stop once the concrete has cured. The structure is fixed, and from that point forward, it can only deteriorate. Roman concrete works completely differently. When seawater percolates through the material, it triggers ongoing chemical reactions. The salt water dissolves the volcanic ash components, and this creates a mineral called aluminum tobermorite, which grows as interlocking crystal plates throughout the concrete. These crystals actually fill in any cracks or voids that form, making the material stronger and more cohesive over time. The concrete is essentially healing itself. Think about that for a moment. Modern concrete fights a losing battle against water. Every drop that enters a crack makes things worse. Roman concrete actually uses water as a building tool. The very force that destroys our concrete made theirs stronger. It's a completely opposite relationship with the environment, almost as if the Romans had figured out how to make friends with the ocean rather than fighting it. But the volcanic ash alone doesn't explain everything. In 2023, researchers from the Massachusetts Institute of Technology made another stunning discovery. Examining Roman concrete samples from the archaeological site of Privernum in Italy, they found tiny white chunks scattered throughout the material. Previous researchers had assumed these were evidence of sloppy mixing, lumps of calcium that hadn't been properly incorporated. The MIT team discovered something very different. These white chunks, called lime clasts, were actually a deliberate feature. The Romans used a technique called hot mixing, where they combined quicklime directly with the pozzolanic ash and water rather than first slaking the lime into a paste. This produced an extremely hot and energetic reaction, reaching temperatures that may have exceeded several hundred degrees, and created those characteristic lime clasts throughout the concrete. And here's the brilliant part. When cracks eventually form in the concrete and water enters, it dissolves these lime clasts. The dissolved calcium then recrystallizes and fills the crack, effectively gluing the concrete back together. The material has a built-in self-repair mechanism, like a biological immune system for stone. The MIT researchers tested this by creating concrete using the Roman hot mixing technique, then deliberately cracking it and running water through it. Within 2 weeks, the cracks had completely healed. Modern concrete samples treated the same way showed no healing at all. The ancient technique genuinely works, and it works remarkably well. Now you might be wondering, if Roman concrete is so superior, why don't we just use it? The answer is complicated. Roman concrete does have real limitations. It takes much longer to reach full strength than Portland cement concrete. Modern construction depends on concrete that hardens quickly and can bear loads within days. Roman concrete achieved its strength over months and years. For a civilization that built massive projects over decades using slave labor, that wasn't a problem. For modern construction schedules, it would be a serious obstacle. Roman concrete is also weaker in terms of compressive strength compared to the best modern mixes. Modern high-performance concrete can withstand enormous loads, which is critical for skyscrapers and bridges. Roman concrete's advantage isn't raw strength, but rather incredible durability and resilience over time. You could think of it like the difference between a sprinter and a marathon runner. Modern concrete wins the sprint, but Roman concrete wins the marathon by a margin of centuries. That said, researchers around the world are now racing to incorporate Roman principles into modern materials. Several companies and university labs are developing self-healing concrete that includes capsules of healing agents, bacteria that produce limestone, or materials inspired by the Roman lime-clast mechanism. The goal is to create concrete that has the quick-setting strength of Portland cement, but the long-term durability of the Roman recipe. There's also a massive environmental incentive. The production of Portland cement is one of the largest sources of carbon dioxide emissions on the planet, responsible for roughly 8% of global carbon emissions. That's more than the entire aviation industry. Much of this comes from the extreme heat required to produce clinker, the key ingredient in Portland cement, with kilns reaching temperatures of around 1400 degrees Celsius. Roman-style concrete, which relies on volcanic ash and lime, requires significantly less energy to produce. Finding ways to replace even a portion of Portland's cement with pozzolanic materials could have an enormous impact on climate change. Some modern engineers are already using volcanic ash and similar materials as supplementary ingredients in concrete. Fly ash from coal power plants, blast furnace slag from steel production, and natural pozzolans are all being incorporated into concrete mixes to improve durability and reduce carbon footprint. These approaches don't fully replicate the Roman recipe, but they're moving in the right direction. What makes the Roman concrete story so compelling is what it tells us about progress. We tend to assume that newer automatically means better, that ancient people were primitive and modern technology is always superior. Roman concrete shatters that assumption. A civilization that didn't understand chemistry at the molecular level, that had no electron microscopes or computer simulations, that relied on observation and trial and error over generations, developed a material that we still cannot fully replicate despite all our technological advantages. They discovered through patient experimentation what took us advanced particle physics to even begin to explain. The Romans didn't just build things, they built things that lasted. And perhaps that's a lesson worth taking seriously. In our era of planned obsolescence and disposable infrastructure, there's something profound about a culture that invested in permanence. Every Roman road, every aqueduct, every harbor wall that still stands is a quiet argument for building things right, for thinking in centuries rather than quarterly reports. Scientists are still unlocking the secrets embedded in those ancient structures. Each new study reveals another layer of sophistication in what the Romans achieved. And with every discovery, we get a little closer to combining the best of ancient wisdom with modern capability. The concrete of the future might just look a lot like the concrete of 2,000 years ago. Sometimes the way forward is to look back.